In 2022, astronomers pointing the James Webb Space Telescope at the ancient universe got results that stopped the room. The galaxies coming back in the data were enormous, fully formed, blazing with hundreds of millions of stars. And they existed when the universe was barely 200 million years old. Every model built over the past 100 years said that was impossible. The chemistry was not ready. The physics had no time. Heavy elements that take generations of dying stars to create were already there, embedded in light that had been traveling since nearly the beginning of time. If you enjoy this kind of content, subscribe and stay with us. What this telescope found raises a question that has no comfortable answer. What else have we gotten wrong? The telescope took 30 years to build, $3 billion, 2 decades of budget crises so severe that Congress voted to cancel the project in 2011, and only a last-minute Senate reversal kept it alive. The mirror required 18 hexagonal gold-coated beryllium panels, each polished to tolerances measured in nanometers, a nanometer being 1/1000th of a meter, roughly 10 times smaller than a hydrogen atom. Engineers achieved that precision on panels together, forming a mirror more than 6 meters across, then folded that mirror into a rocket and trusted it to unfold in deep space without a single error. The sunshield required 5 separate membrane layers the size of a tennis court to protect the telescope from solar heat, and those layers had to fold into a rocket fairing and then unfold using 344 separate release mechanisms, each of which had to fire without failure. If even one stuck, the telescope would never cool to operating temperature and the mission would end. There was no repair option. The James Webb Space Telescope would operate 1 million miles from Earth, 4 times farther than the Moon, beyond the reach of any crewed spacecraft ever built. When the telescope cleared its launch tower on Christmas morning of 2021, rising above the jungle coast of French Guiana on an Ariane 5 rocket, the sound from mission control was captured on camera and has been replayed thousands of times since. It was not the composed professional satisfaction you might expect from scientists finishing a successful launch. It was an audible, collective exhale. A generation of researchers who had devoted careers to this machine, who had watched it nearly cancelled, who had staked professional legacies on what it might find, were breathing out after 20 years of held breath. Over the 6 months that followed, every deployment stage executed without a failure. The sunshield's 344 mechanisms all fired correctly. The mirror segments aligned using actuators, capable of movements smaller than the width of a human hair. The instruments cooled to within a few degrees of absolute zero, where thermal noise drops low enough for detectors to catch photons that have been traveling for nearly 14 billion years. By the summer of 2022, science operations were fully underway, and the images coming back were unlike anything any telescope had produced. Webb observes primarily in infrared light, the long wavelength radiation beyond the red edge of the visible spectrum. Infrared is the key to seeing the ancient universe because of a fundamental consequence of cosmic expansion. When a galaxy billions of light years away emits light, that light spends billions of years crossing the expanding cosmos. The expansion itself stretches the light's wavelength during its journey, shifting it from shorter visible wavelengths into longer infrared wavelengths that human eyes cannot detect. The farther the light has traveled, the more it has been stretched. The most ancient galaxies, from the universe's first few 100 million years, have had their light shifted so completely into the infrared that they are invisible to any optical telescope. Hubble Space Telescope was primarily an optical and ultraviolet instrument. It could see the near-infrared, but not deeply into it. The light from the universe's first galaxies was essentially invisible to Hubble. Webb was designed specifically for that light. Its mirror is 7 times larger in collecting area than Hubble's. It operates far from Earth's heat glow. Its instruments are precisely calibrated to the infrared wavelengths of the most redshifted ancient galaxies. When it finally aimed those instruments at the oldest, deepest fields of sky it could find, The data it returned changed the character of cosmology permanently. The scientific community had prepared a confident prediction for what Webb would find. That prediction rested on the most successful cosmological framework in history, one that had passed every previous observational test. The prediction said the earliest universe should be humble, small, dim, irregular, chemically bare, galaxies barely beginning to form. When the first deep field science data came back, the prediction was wrong in ways nobody had fully anticipated, and the wrongness ran deeper with every subsequent dataset. The standard model of cosmology that generated those predictions is called Lambda CDM, and it deserves to be understood before you can appreciate what JWST has challenged within it. Lambda is the mathematical symbol for the cosmological constant, the mathematical description of dark energy, the mysterious force permeating all of empty space and causing the universe to expand at an accelerating rate. CDM stands for cold, dark matter, the invisible gravitationally active substance composing roughly 27% of the cosmos. Ordinary atomic matter, everything we can see, touch, weigh, and build instruments from, makes up only about 5% of the universe's total energy and mass content. Dark energy accounts for 68%. Together, these three components define a universe where gravity builds structure at small scales, while dark energy, acting on the largest scales, slowly drives those structures apart. Lambda CDM is not a rough guess or a provisional placeholder waiting for something better. It is the product of 5 decades of observational tests, spanning vastly different physical scales and phenomena. The model correctly predicts the detailed temperature fluctuations in the cosmic microwave background. The ancient light released 380,000 years after the Big Bang, with precision down to fractions of a percent across dozens of independent angular scales. It correctly predicts the ratio of hydrogen to helium produced in the first 3 minutes of cosmic history, a ratio that has been measured in the most chemically primitive stars and gas clouds in the observable universe, and agrees with the model to better than 1%. It describes the three-dimensional distribution of galaxies across billions of light-years in striking agreement with large galaxy surveys. It explains the growth of cosmic structure from tiny primordial fluctuations to the enormous filaments and voids visible in the cosmic web today. This is not a model under routine scientific scrutiny. It is a framework that has earned its central position through repeated, independent, high-precision confirmation across nearly every class of cosmological observation available. The part of Lambda CDM under stress from JWST is not its description of dark energy or its account of the universe's large-scale geometry. Those aspects remain robustly confirmed. The pressure falls specifically on the model's description of how galaxies form and grow, a subfield called galaxy formation theory that operates within the Lambda CDM cosmological framework. Galaxy formation in Lambda CDM follows a principle called hierarchical assembly. Gravity amplifies the tiny density fluctuations seeded throughout space in the universe's first fractions of a second. The slightly overdense regions pull surrounding matter toward them and grow denser still. Dark matter halos, spherical concentrations of invisible matter, form first and earliest at the peaks of these density fluctuations. Ordinary baryonic matter, the atoms that make up gas and stars, falls into those halos, cools, and begins forming stars. The process is hierarchical because small halos assemble before large ones. Small fluctuations reach gravitational collapse faster than large ones because the gravity signal has less distance to travel. Small galaxies precede large ones. Large galaxies, like the Milky Way, are late arrivals, assembled through billions of years of mergers and slow accretion of smaller predecessors. This hierarchical picture makes a specific quantitative prediction for the first galaxies. They should be small. The dark matter halos available in the first few 100 million years are too small to host massive galaxies. The baryonic mass they contain is limited. The star formation that can occur in those halos is constrained by the amount of available gas and the physical processes that regulate how efficiently that gas converts to stars. The first galaxies should be tiny by modern standards, chemically nearly empty, because the stellar generations needed to produce heavy elements have barely begun their work, and structurally irregular because orderly disk galaxies need billions of years of stable evolution to assemble. Every simulation of early galaxy formation within Lambda CDM produces this picture consistently. It is a precise prediction from a well-tested framework, and it is what Webb has found to be significantly wrong. The timeline the Big Bang model prescribes for cosmic history is the foundation on which every expectation about early galaxies rests. 13.8 billion years ago, everything that exists emerged from a state of incomprehensible density and temperature. Not an explosion of matter into pre-existing space, but the beginning of space itself, expanding outward from a condition so extreme that the known laws of physics break down when you try to describe it mathematically. In the first few minutes, nuclear reactions in the cooling, expanding fireball produced hydrogen nuclei, helium nuclei, and trace amounts of lithium from the sea of protons and neutrons. No heavier elements formed. The conditions were right for nuclear fusion in those first minutes, but the universe was expanding and cooling too fast for the reactions to proceed to heavier nuclei. The Big Bang locked the universe's initial chemical inventory in place, roughly 75% hydrogen and 25% helium by mass, with only the tiniest trace of anything heavier. For the next 380,000 years, the universe was an opaque plasma. The temperature was too high for electrons to attach to nuclei and form neutral atoms. Every photon that tried to travel was almost immediately scattered by a free electron. Light was trapped, bouncing endlessly in every direction, carrying no information about what was happening on any scale. The universe during this phase was opaque in a way that makes the densest fog on Earth seem transparent by comparison. No instrument could have observed it from the outside, even if instruments had existed. Then, as the expanding universe cooled below approximately 3,000 degrees, something happened simultaneously everywhere. Electrons attached to protons throughout the cosmos at essentially the same moment, forming neutral hydrogen atoms in a transition astronomers call recombination. The plasma cleared, light streamed freely for the first time in history. The ancient glow of that transition still fills the entire sky today as the cosmic microwave background, arriving from every direction with a temperature of just under 3 degrees above absolute zero, after 13.8 billion years of cosmic expansion, have shifted its wavelength from infrared into microwaves. Tiny variations in the cosmic microwave background temperature across the sky, differences of only 1 part in 100,000, encode the density fluctuations that seeded all future structure. Regions that were slightly denser than average when the plasma cleared were the seeds of future galaxy clusters. Regions slightly less dense became the great cosmic voids. The Planck satellite measured those variations with extraordinary precision, and they matched the Lambda CDM model's predictions almost perfectly. This agreement between the ancient microwave background and the model's predictions is one of the most powerful confirmations of the standard framework available. It means that whatever the model predicts for what developed from those seeds in the subsequent billions of years carries the weight of one of the most precise measurements in all of science. What the model predicts from those seeds, for the universe's first few 100 million years, is now what JWST is testing directly. The seeds were small. Small fluctuations produce small halos first. Small halos host small galaxies. The first galaxies should be faint and chemically bare. That is the prediction. That is what the plasma clearing moment encoded for the universe's future, according to a model that has been validated against the plasma clearing signal with extraordinary precision. The problem is that the early universe, encoded in that ancient light, appears to have produced something very different from what the model says those seeds should have grown into. And the evidence for that difference arrived in data that was confirmed by multiple independent teams, using multiple independent methods, leaving no room for it to be a measurement artifact. After recombination came the cosmic dark ages, a period that deserves the drama of its name. For roughly 200 million years after the plasma cleared, the universe contained no stars anywhere. No light was being generated. The microwave background glow was fading and cooling as the universe expanded. Vast clouds of neutral hydrogen and helium gas drifted through the dark, cooling toward temperatures just a few degrees above absolute zero. Gravity was working on those clouds, pulling the slightly denser regions inward while the emptier voids grew emptier still. But the effects were slow and invisible. The dark matter, which does not interact with electromagnetic radiation and had been free to begin gravitational assembly even while the baryonic plasma was opaque, had been accumulating into halos long before the plasma cleared. By the time recombination happened and the plasma fog lifted, dark matter halos of various masses already existed, and the baryonic gas began falling into them for the first time. The Dark Ages were not dramatic in any way a human observer would recognize. They were a period of patient, invisible construction proceeding without sound or light, driven by nothing more exciting than the slow accumulation of hydrogen gas toward gravity wells sketched by invisible matter. No star, no galaxy, no light source of any kind interrupted the darkness. The universe existed for 200 million years in a state of absolute, perfect, featureless dark. The darkness ended when the first stars ignited. Astronomers call these objects population 3 stars, a name that reflects when the category was classified rather than their chronological position as the universe's first. They formed from gas containing only hydrogen and helium, with no trace of any heavier element. The absence of metals altered their cooling behavior during collapse in a way that may have favored the formation of extremely massive objects, potentially hundreds of times more massive than our own star. At those masses, they burned at temperatures far higher than modern stars, producing floods of ultraviolet radiation energetic enough to ionize hydrogen atoms across huge volumes of space. This process, called cosmic reionization, gradually converted the neutral hydrogen fog that had settled during the Dark Ages back into a plasma of free electrons and protons, reionizing the entire universe over a period of several 100 million years. Population 3 stars lived perhaps 1 million years, burning through their hydrogen fuel at a ferocious rate. When they died violently in supernova explosions, more energetic than those produced by any subsequent stellar generation. Those explosions scattered the first heavy elements into surrounding space for the first time in cosmic history. Carbon appeared, oxygen appeared, nitrogen, silicon, sulfur, magnesium, and iron appeared. Every heavy element that would later form planets, build chemistry, and underpin biology was being created for the first time in those ancient detonations. The material ejected by population 3 supernovae mixed into surrounding gas clouds, enriching them with metals. The second generation of stars formed from this slightly enriched gas and was smaller and longer lived than its predecessors. The third generation, smaller still, galaxies began to assemble around dark matter halos, gravity collecting stars and gas into loosely bound structures that would grow and merge across billions of years into the galaxies visible today. The whole process was supposed to be slow and hierarchical and long. The chemical enrichment needed to produce the heavy element abundances seen in modern galaxies was supposed to require billions of years of stellar generations. The structural maturity seen in modern disk galaxies was supposed to require billions of years of settling. The sheer mass of modern massive galaxies was supposed to require billions of years of mergers. JWST is finding that the early universe skipped most of that waiting period. The question is why, and what the answer means for everything we thought we understood. The specific, quantitative prediction lambda CDM makes for early galaxy formation is precise enough to test directly, and it is this precision that makes JWST's findings so scientifically significant. Computer simulations of cosmic structure formation, run using the lambda CDM model's equations on the world's most powerful supercomputers, consistently produce the same picture of the universe's first few 100 million years. Dark matter halos of various masses form in a hierarchy determined by the spectrum of primordial density fluctuations. Gas falls into those halos, cools, and forms stars. The first galaxies, defined as the first gravitationally bound systems with active star formation, appear around 100 to 200 million years after the Big Bang. But they are small. At 200 million years, the most massive galaxies in a standard simulation hold perhaps 10 to 50 million solar masses of stars. At 500 million years, the most massive hold perhaps a few 100 million solar masses. At 1 billion years, a small number of especially fast-growing galaxies might reach a few billion solar masses. These predictions come with a physical justification. The maximum mass of any galaxy at any epoch is limited by the mass of the dark matter halo hosting it, because the halo's gravitational potential determines how much gas can be collected. At early times, the largest halos that exist are not very massive, because the hierarchical assembly process has not had enough time to build large halos through mergers. Additionally, the efficiency of star formation, the fraction of available gas that actually converts to stars, is limited by feedback processes that operate in all star-forming environments. The radiation and winds from massive stars heat surrounding gas and suppress further star formation, and supernova explosions expel gas from galaxies entirely. The combination of limited halo mass and feedback-limited star formation efficiency produces the prediction of small, modest, first galaxies. Those simulations had never been tested against observations of galaxies at the extreme redshifts Webb can reach. Previous telescopes could observe some galaxies at high redshifts, but with much lower resolution and sensitivity, and at lower redshifts than Webb achieves. The expectation going into the Webb mission was that these simulations, refined over decades and tested against every previously available observation, would describe the universe Webb found correctly. That expectation was wrong. What made the confrontation between prediction and observation possible was Webb's unique combination of sensitivity, infrared coverage, and resolution. Earlier telescopes could detect the most luminous early galaxies, essentially the brightest outliers in the early universe galaxy population, but could not characterize the typical galaxy population at those epochs. Webb can see far fainter and farther. It is detecting not just the brightest early galaxies, but a statistically representative sample of the full galaxy population at high redshifts, and that population is systematically different from what the simulations produce. The difference is not ambiguous or marginal. The early universe galaxy population observed by Webb is brighter, more massive, and more numerous at the high mass end than any standard simulation predicted. The discrepancy grows larger at higher redshifts, meaning the farther back in time Webb looks, the more the observations deviate from predictions. That trend, a discrepancy that increases with look-back time, is exactly the opposite of what you would expect from measurement errors that should be scale-independent. It suggests that the model is wrong in a specific way that becomes more apparent the earlier in cosmic history you look. The single most dramatic confirmed example of the anomaly is a galaxy designated JWST 14, found within the data of the JD survey, one of Webb's flagship deep imaging programs that committed hundreds of telescope hours to building extremely deep images of carefully selected sky patches. This galaxy was confirmed in 2024 through spectroscopic analysis led by astronomer Stefano Carniani and his collaborators. Spectroscopy is the gold standard in cosmological distance measurement. Rather than estimating a galaxy's distance from the color distribution of its light, spectroscopy breaks that light into its component wavelengths and identifies the specific emission lines from known atomic transitions. These lines have known wavelengths in laboratory settings. When they appear in a galaxy's spectrum, they are shifted to longer wavelengths by the expansion of the universe during the light's travel time. The ratio of the observed wavelength to the laboratory wavelength gives the redshift, and from the redshift, cosmologists can calculate the precise time in cosmic history when the light was emitted. 4. JWST. The confirmed spectroscopic redshift placed this galaxy in time when the universe was approximately 290 million years old. 290 million years is 2% of cosmic history. The universe at this moment was the cosmic equivalent of a 2-year-old child. Standard model simulations running forward from the Big Bang produced no galaxy with a stellar mass above perhaps 10 million solar masses at this epoch. JWST 140 holds more than 500 million solar masses of stars packed into a region roughly 1,600 light-years across, and it is actively forming new stars at a rapid rate. The discrepancy between the model's prediction and the observation is a factor of 50. Every independent team that analyzed the data arrived at the same conclusion. The galaxy is real, its distance is confirmed, and its mass is roughly 50 times higher than the most generous standard model prediction for its epoch. The size of the discrepancy matters for how it can be interpreted. A factor of 2 might suggest a calibration issue or a poorly understood systematic bias in the mass estimate. A factor of 5 might indicate that the simulations need refinement in their feedback prescriptions. A factor of 50 leaves no comfortable explanatory room within the existing framework. It means the early universe was assembling stellar mass at a rate so much faster than models predict that any resolution requires either fundamentally different physics or a significant modification of the model's description of how dark matter halos accumulate gas and convert it to stars. The mass of JWST would have been sufficient on its own to reshape cosmological priorities. But the spectrum that confirmed its distance also revealed something that made a serious problem into a crisis. Multiple independent teams, working separately on the same dataset, using different analysis codes, all found the same thing buried in the spectrum: the fingerprint of oxygen. Oxygen does not come from the Big Bang. This is not a subtle or contested point of cosmological theory. The Big Bang produced hydrogen, helium, and traces of lithium, and nothing else. Every oxygen atom anywhere in the universe was manufactured inside a star. It was forged through nuclear fusion in a stellar core. It was locked inside that star for the entirety of the star's lifetime. It was scattered into surrounding space only when the star died and exploded as a supernova. There is no pathway from the Big Bang directly to oxygen that does not pass through a star living and dying. For oxygen to be detectable in a galaxy at 290 million years after the Big Bang, a specific sequence of events had to complete. First, gas clouds had to collapse and form the first stars. That collapse takes tens of millions of years as gas cools and falls toward density peaks. Then, among those first stars, some had to be massive enough to produce oxygen through nuclear fusion in their cores. The most massive stars are the ones that make oxygen quickly, and they live for roughly 1 million years before dying as supernovae. Their explosion must scatter oxygen-rich material into surrounding space. That material must then mix back into new gas clouds over timescales of tens of millions of years. Those clouds must then collapse into a new generation of stars. Only in that second generation, forming from gas enriched by the first generation's deaths, would the oxygen fingerprint become detectable in a galaxy's spectrum. The minimum time for this full cycle, from first star ignition to detectable oxygen in the next generation, is roughly 50 to 100 million years, under the most optimistic physical assumptions about how fast gas collapses, how fast supernovae eject a mix, and how fast new clouds form. Fitting that cycle into the period before 290 million years after the Big Bang is possible if every stage runs at its physical maximum simultaneously, but it leaves almost no margin. The timeline squeezes the standard model against its hard limits. What makes the oxygen in JWST 140 the earliest confirmed detection of any heavy element in a galaxy is not just its age. It is the combination of that age with the galaxy's mass. The galaxy already holds 500 million solar masses of stars and contains detectable oxygen. That combination requires not just that one cycle of stellar enrichment completed, but that the galaxy assembled and processed an enormous quantity of gas quickly enough to reach that mass while also completing the enrichment cycle. The two constraints together are tighter than either alone. Scientists who study stellar populations and chemical evolution have modeled the earliest possible enrichment timeline in the early universe. The consensus is that the oxygen signal in JWST 140, while physically possible under extreme assumptions, represents the universe operating at the outer limits of what the known physics of star formation and stellar evolution can support. The early universe was not warming up slowly to the business of chemistry. It was running the full chemical factory essentially from the start, at a pace that the standard model assigns to a time more than 1 billion years later. The pattern of anomalous early massive galaxies began with individual discoveries, but became a statistical crisis when researchers examined the full population. In the summer of 2022, astronomer Stephen Finkelstein was examining the very first public JWST science images when he noticed a galaxy that stood out immediately from everything around it, too bright for its position, too luminous for anything the standard model predicted at that apparent distance. He named it Maisie's Galaxy, after his daughter, a naming choice personal enough to humanize one of the most cosmologically significant objects ever identified. Photometric estimates placed the galaxy at roughly 390 million years after the Big Bang, a redshift near 11.5. Photometric redshifts, measured from the color distribution of an object's light across several broad wavelength bands, are estimates that carry real uncertainties. The community waited for spectroscopic confirmation before drawing strong conclusions. Spectroscopic follow-up came in 2023 and verified the distance with precision. Maisie's galaxy was exactly where its colors had suggested. With the distance confirmed, the brightness anomaly was confirmed along with it. The galaxy was shining with a luminosity that required either far more stars than standard models predicted for its epoch, or far more efficient star formation, or both. The spectroscopic confirmation did not resolve the brightness problem. It locked it in. Maisie's galaxy entered the formal scientific literature at a moment when the broader community was beginning to recognize that it was not an isolated outlier. Deep field surveys in multiple sky regions were returning similar results across the full population of early galaxies. The pattern was not a few extreme objects standing above a population that otherwise matched predictions. The entire distribution was shifted. The typical early galaxy in JWST data was more luminous and more massive than the typical early galaxy in any standard simulation. The problem was systematic rather than episodic. What also distinguished Maisie's galaxy from some earlier anomalous candidates was the speed of its confirmation. Some high redshift galaxy candidates identified before JWST's launch required years of follow-up with multiple telescopes before their distances were secured. JWST's capabilities, particularly its ability to obtain spectroscopy of faint, high redshift galaxies in reasonable observing times, meant that the confirmation pipeline was much faster. Candidates identified in 2022 were confirmed in 2023. The accumulation of confirmed anomalies happened not over decades but over months. The community did not have time to process one surprising result before the next one arrived. By the end of 2022, the first season of JWST science data had produced enough confirmed high redshift galaxies to make a statistical statement about the early universe galaxy population. The statement was uncomfortable for the standard model. At every redshift above 5, the observed number of massive galaxies exceeded the model's prediction, and the excess grew larger at higher redshifts. At redshifts above 10, where the universe was less than 500 million years old, The excess was large enough to qualify as a significant tension between observation and prediction by any standard scientific metric. The formal quantification of the tension came in two landmark papers published in 2023. The first, by astronomer Ivo Labbé and collaborators in the journal Nature, reported the identification of 6 candidate galaxies in the first 700 million years of cosmic history, with apparent stellar masses comparable to or exceeding the Milky Way. The Milky Way contains roughly 60 billion solar masses of stars assembled over nearly its full 13 billion year history. Finding candidates with comparable mass at a time when the universe was barely 5% of its current age set off an immediate reaction in the scientific community and in science journalism. The objects were called universe breaker galaxies, a label dramatic enough to attract broad attention and physically specific enough to be taken seriously by researchers who understood what a universe-scale violation of standard predictions would mean. The Labbé candidates were photometric, meaning their distances were estimated from color data rather than confirmed spectra. The paper was careful about this limitation and explicitly framed the findings as requiring follow-up spectroscopic confirmation before strong conclusions could be drawn. Some of the most extreme candidates were subsequently revised downward in stellar mass when follow-up spectroscopy revealed active galactic nuclei, contributing significantly to the observed luminosity in a few objects. Nuclear emission from a feeding central black hole shines in infrared wavelengths, similar to those used to estimate stellar mass from photometry, and if that nuclear emission is misidentified as starlight, the stellar mass estimate can be inflated substantially. But the revision of the most extreme outliers did not erase the statistical signal. The broader population of early massive galaxy candidates in JWST data remained systematically more massive than standard model predictions, even after the confirmed AGN-contaminated sources were removed. The excess was not created by a handful of extreme objects biasing the statistics. It was distributed across the full population. Independent research groups analyzing different JWST survey fields found the same excess. Teams using different analysis methods and different assumptions about stellar populations found the same excess. The consistency of the signal across independent analyses made it extremely difficult to attribute to any systematic bias in the measurements. The second landmark paper came from Mike Boylan-Colchin at the University of Complies, Texas. Published in Nature Astronomy, it performed a rigorous statistical analysis of what the most extreme JWST galaxy candidates implied for the Lambda CDM framework. Boylan-Colchin calculated the maximum stellar mass that the model could accommodate at each early epoch, given realistic constraints on dark matter halo mass functions and baryon fractions. He then placed the JWST observations against those theoretical limits. The result was a quantified probability. For the most extreme candidates to exist within the standard model, the efficiency of star formation in the early universe would have had to approach 100%. Standard stellar physics forbids this. Feedback from massive stars, both through radiation during their lives and through explosions at their deaths, limits real star formation efficiency to a few percent in most environments, and to perhaps 30% in the most extreme starburst conditions. 100% efficiency would require these feedback processes to not operate. Observations across hundreds of thousands of star-forming regions throughout the nearby universe confirm that feedback does operate. The tension was not a subtle statistical artifact. It was a hard physical contradiction between what the model could produce and what Webb was finding. The anomaly in early galaxy masses was further complicated by what those galaxies contained chemically. Metallicity, the abundance of elements heavier than hydrogen and helium in astronomical nomenclature, is a tracer of stellar history. Every heavy element in a galaxy required at least one stellar generation to have lived and died, forging that element in its core and scattering it into space. The more heavy elements a galaxy contains, the deeper its stellar history. A chemically enriched galaxy is a galaxy that has already processed significant quantities of gas through multiple generations of stars. Standard models predict that early galaxies should be nearly metal-free. In the first few 100 million years of cosmic history, stellar generations have barely begun accumulating. The chemical enrichment of galactic gas is supposed to proceed slowly over billions of years, building gradually as each stellar generation contributes its nucleosynthetic products. Early galaxies should show the simplest chemistry, hydrogen and helium, with only the faintest traces of anything heavier, and those traces mostly from the very first stellar generation. JWST's spectroscopic data on early galaxies consistently shows higher metallicities than these predictions allow. Galaxies in the first 500 million years frequently show detectable oxygen, carbon, and nitrogen at levels that standard models assign to galaxies more than 1 billion years old. GN Z11, a galaxy at roughly 430 million years after the Big Bang, first discovered by Hubble and studied in extraordinary detail by JWST, shows nitrogen levels in the gas surrounding its central black hole that are dramatically above any standard enrichment model. Multiple independent teams analyzing GN Z11 confirmed the nitrogen signal and found no standard explanation for it. The nitrogen abundance implied either an unusual enrichment pathway, perhaps involving tidal disruption events stripping stellar material near the black hole, or a stellar population that had already processed far more gas through multiple enrichment cycles than should have been possible at that epoch. The metallicity problem is not unique to individual extreme objects. It appears as a population trend. Early JWST galaxies are statistically more chemically enriched than standard models predict at every high redshift examined. The chemical clock of the early universe was running faster than any simulation had reproduced. Star formation was occurring faster than predicted, and the full chemical processing cycle, from first star formation through multiple stellar generations to detectable heavy element abundances, was completing on timescales that the standard model had no mechanism to explain. This convergence of anomalies, too much stellar mass, too much chemical enrichment, at the same early epochs, points toward a universe that was more efficient at assembling and processing matter in its first few 100 million years than any model predicted. The direction of every discrepancy is the same. The early universe was more mature, more active, and more chemically complex than the theory allowed. That consistency across multiple independent observational probes is the signature of a systematic gap in the theoretical framework, not a collection of unrelated measurement errors. At the centers of many early JWST galaxies, a third major anomaly was waiting to be revealed. Supermassive black holes, the gravitational monsters that lurk at the hearts of most large galaxies, appeared in the earliest JWST observations at masses that violated every known model of black hole growth. The black holes found at the centers of galaxies in the first 500 million years of cosmic history were too massive too soon, just as the galaxies themselves were too massive too soon. To understand why, you need to know how black holes grow. A stellar mass black hole, the kind that forms when a massive star collapses, starts with a mass of perhaps 10 to 100 times that of our star. Growing from that seed to a supermassive black hole with millions or billions of solar masses requires accreting an enormous quantity of gas over time. As gas falls toward a black hole, it forms a swirling accretion disk that heats to extreme temperatures and radiates powerfully across multiple wavelengths. The radiation from that infalling material exerts pressure on surrounding gas, pushing back against further accretion. At a specific accretion rate called the Eddington rate, the outward radiation pressure exactly balances the inward gravitational pull on new infalling gas, limiting how fast the black hole can grow. This limit is not a model assumption. It is derived directly from the balance between gravity and radiation pressure, two of the most precisely understood forces in physics. starting from a stellar remnant black hole at the beginning of the universe and growing at exactly the Eddington rate continuously without interruption. You can reach perhaps 1 billion solar masses by 500 million years after the Big Bang. That sounds achievable until you consider what continuously, without interruption, means in practice. Real black holes do not accrete at maximum rate constantly. Their gas supply is intermittent. Feedback from their own radiation periodically disrupts surrounding gas and cuts off accretion. Mergers and other dynamical events can temporarily halt growth. The realistic growth trajectory for a black hole starting from a stellar remnant seed falls far short of the theoretical maximum, making billion solar mass black holes at 500 million years after the Big Bang vanishingly improbable under standard models. JWST, often in combination with X-ray data from other observatories, found these vanishingly improbable objects in substantial numbers across the early universe. Several specific examples stood out. UHZ1, found at roughly 450 million years after the Big Bang, in a collaboration between JWST and the Chandra X-ray Observatory, harbors a black hole estimated between 10 million and 1 billion solar masses, potentially representing a significant fraction of the entire galaxy's stellar mass. In a mature galaxy, the central black hole is typically a tiny fraction of the stellar mass. Finding a black hole representing a large fraction of the galaxy mass this early implies either a different formation pathway entirely or a growth rate far exceeding the Eddington limit in ways standard physics does not easily accommodate. GN-Z11 at 430 million years after the Big Bang shows a feeding black hole alongside the nitrogen anomaly already discussed. CERS 1019 at roughly 570 million years harbors a black hole of approximately 1 million solar masses already accreting actively. The black hole problem and the galaxy mass problem share the same character. The early universe was building massive objects, both stellar and not, at rates that the standard model had no mechanism to produce. The black hole growth problem crystallized most dramatically in a single galaxy that combined X-ray and infrared observations in a way that left no room for alternative interpretation. UHZ1 was found by combining data from two separate space observatories, the James Webb Space Telescope, which identified it as a high redshift galaxy in the infrared, and the Chandra X-ray Observatory, which detected powerful X-ray emission from its center. The X-ray signal is the unmistakable signature of hot gas being heated to tens of millions of degrees as it falls toward a black hole. The energy of infall converted to radiation that shines across the entire X-ray spectrum. When the team calculated the mass of the black hole producing those X-rays, the answer fell between 10 million and 1 billion solar masses, at a redshift, placing the galaxy approximately 450 million years after the Big Bang. Understanding why UHC1 is so disturbing requires understanding the relationship between black holes and the galaxies they inhabit. In a mature galaxy like the Milky Way, the central black hole is a minor mass contributor. Sagittarius A star, the black hole at the center of our galaxy, has a mass of roughly 4 million times that of our own star. The galaxy surrounding it holds approximately 60 billion solar masses of stars. The black hole is less than 1/100th of 1% of the total stellar mass. This ratio, with the black hole being a tiny fraction of the surrounding galaxy, is observed consistently throughout the local universe and interpreted as evidence of the co-evolutionary relationship between black holes and galaxies. They grow together in a regulated feedback dance, with the black hole's radiation and jets limiting star formation and the galaxy's gas supply limiting black hole growth. Both participants in this dance grow slowly and in proportion to each other over billions of years. In UHZ1, the black hole appears to represent a substantial fraction of the galaxy's total stellar mass, not the tiny fractional contribution seen in mature local galaxies, but a dominant gravitational player already competing with the stellar population for gravitational significance. This implies that either the black hole formed through a completely different mechanism than the standard stellar remnant pathway, bypassing the need to grow slowly from a small seed, or that the black hole grew at rates far exceeding the Eddington limit in ways that standard physics does not predict or permit. The most widely discussed alternative pathway is called direct collapse. Under specific conditions in the very early universe, a massive gas cloud might bypass the star formation phase entirely and collapse directly into a black hole with hundreds of thousands or even millions of solar masses from the start. The conditions required for direct collapse are stringent. The cloud must be free of heavy elements. It must be exposed to sufficient ultraviolet radiation to prevent cooling and fragmentation, and it must be in a region with enough gas to sustain collapse without forming stars along the way. These conditions are theoretically possible, but were expected to be rare. What JWST is showing is that whatever mechanism produces massive early black holes is apparently common rather than rare, which requires either a wider prevalence of direct collapse conditions than expected or some additional formation pathway not yet incorporated into standard models. GN-Z11 occupies a special place in the catalogue of early universe mysteries because it compounds several anomalies simultaneously in a single object. This galaxy, located at approximately 430 million years after the Big Bang, was originally discovered by the Hubble Space Telescope and was at one point the most distant galaxy known. JWST returned to it with significantly greater sensitivity and spectroscopic capability and revealed a complexity that Hubble could not have detected. At the center of GN-Z11 is an active galactic nucleus, a feeding black hole of approximately 6 million solar masses consuming surrounding gas and shining brilliantly across multiple wavelengths. At 430 million years after the Big Bang, a 6 million solar mass black hole is already in tension with standard growth models. But the mass alone is not the most surprising thing about GN-Z11. What attracted the most attention from the spectroscopic data was the chemical composition of the gas surrounding the black hole. The gas shows elevated nitrogen levels, dramatically above what any standard model of early chemical enrichment can explain. Nitrogen is not the same as oxygen in terms of stellar production pathways. While oxygen is produced quickly in the cores of massive stars that live and die on timescales of millions of years, nitrogen is primarily produced by intermediate mass stars during a late evolutionary phase called the asymptotic giant branch. These stars are less massive than the giants that produce oxygen quickly. They live for hundreds of millions of years before reaching the phase that produces significant nitrogen. Finding elevated nitrogen in GN-Z11 at 430 million years after the Big Bang means that a substantial population of intermediate mass stars had already completed their entire evolutionary cycle by that point, including the lengthy main sequence phase that takes hundreds of millions of years. The timeline implied by the nitrogen abundance does not fit comfortably into any standard model of early galaxy formation. Multiple independent teams analyzed the GN-Z11 spectroscopic data and confirmed the nitrogen signal was real, not an artifact of noise or calibration. Multiple explanations were proposed. Some researchers suggested that tidal disruption events, in which stars get ripped apart by the black hole's gravity, might deliver unusual chemical mixtures to the surrounding gas. Others proposed that dissolving globular clusters near the galactic nucleus could contribute enriched material with different elemental ratios. A few theorists explored whether extreme conditions at very low metallicity might alter stellar nucleosynthesis in ways that produce more nitrogen than normal. None of these explanations achieved scientific consensus. The nitrogen abundance in GN-Z11 remains one of the most discussed unresolved problems in current observational cosmology, a signal from a 430 million year old galaxy that the field has not yet been able to explain. The anomalies JWST has uncovered are not limited to the masses and chemical compositions of early galaxies. They extend to the very shapes of those galaxies. and the shapes tell a story as disturbing as any number in a spectrum. The shapes of galaxies encode their dynamical histories. A chaotic, irregular blob of stars is the shape of something young and unsettled, still accumulating mass through random mergers and accretion events, not yet organized into a coherent dynamical structure. A smooth elliptical ball of old stars is the shape of something that burned through its fuel long ago and settled into a stable configuration of orbiting stars with no preferred plane. A flat, rotating disk, like the Milky Way, is the shape of something that has been stable for a long time, with gas gradually settling into the plane of rotation as angular momentum is conserved through generations of accretion. Standard models predict that disk galaxies should be extremely rare in the first few billion years of cosmic history. The early universe was dominated by mergers. When two galaxies collide and merge, they disrupt each other's disk structures. The angular momentum of the combined system is redistributed through violent gravitational interactions. A disk that forms in one merger is typically destroyed by the next. Building a stable, persistent disk galaxy requires a long period of quiet evolution following the last major merger, with gas settling gradually into rotation without further major disruptions. The Standard Model predicts that this settling process requires many billions of years to produce the prevalence of disk galaxies seen nearby. In the first 2 to 3 billion years of cosmic history, the model predicts that disks should make up perhaps 10% or fewer of the galaxy population. A systematic study, published in 2023, led by astronomer Leonardo Ferreira, and analyzing a large sample of galaxies from the first 3 billion years of cosmic history in JWST data, found that approximately 50% of galaxies in that sample showed clear disk morphology. Flat, organized, rotationally supported structures with properties consistent with rotation-dominated dynamics rather than pressure-supported random stellar orbits. 50% versus the predicted 10% is a factor of 5 discrepancy. That is not a calibration issue or a statistical fluctuation. It is a systematic deviation between observation and theory across a well-defined galaxy population. The implications go beyond the disk fraction statistic. Finding disk galaxies so common so early means either the early universe was far less merger-dominated than models predict, giving disks the stability they need to persist, or disk structures form and stabilize on timescales far shorter than models allow, recovering quickly from disruptions. Both possibilities challenge the Standard Model's picture of the early cosmic environment as a chaotic, merger-saturated landscape in which ordered structures cannot survive. The early universe was apparently more orderly than any simulation had suggested, producing stable, organized galaxies at a time when the theory said nothing of the sort should be possible. Adding to the catalogue of unexplained early universe phenomena, JWST has identified an entirely new class of objects with no clear counterpart in the nearby universe. Appearing in every deep JWST survey, in numbers that no pre-launch simulation predicted, these objects have been given an informal name by the researchers cataloging them: little red dots. Little red dots are compact objects with extremely red colors, appearing predominantly at high redshifts. Their compactness distinguishes them from typical early galaxies of comparable luminosity, but it is their spectra that make them truly puzzling. Some little red dots show narrow emission lines from gas heated by star formation, the kind of lines that appear when young, massive stars ionize surrounding hydrogen clouds. Others show broad emission lines from gas moving at high velocities near a feeding black hole, the kind of lines that appear when material is orbiting rapidly in the deep gravitational potential of an active galactic nucleus. Many appear to show both types of emission simultaneously, which creates an immediate physical puzzle. Narrow emission line regions in galaxies typically span thousands of light-years across the full extent of the star-forming disk. Broad emission line regions in active nuclei are confined to a tiny volume less than a light-year across, the region immediately surrounding the black hole, where orbital velocities are high enough to produce the characteristic velocity broadening. For both signatures to appear at comparable strength from the same object at cosmological distances means either the two physically distinct regions are somehow appearing unresolved by JWST, or one of them is not producing the signal for the expected physical reason, or something else entirely is happening that current models do not describe. Hundreds of little red dots have been catalogued across multiple independent JWST survey programs. No simulation run before JWST's launch produced anything resembling this population. Their existence represents a genuinely new class of object that the universe apparently forms in large numbers at early times, and that the standard model has no established mechanism to explain. Theorists have proposed various scenarios. Extremely compact early galaxies where stellar and nuclear emission overlap spatially. A brief evolutionary phase of simultaneous maximum star formation and maximum black hole accretion in dense environments, or some property of very dense, ultra-compact dark matter halos that creates unusual conditions in the early universe. None of these proposals has been confirmed. The little red dots are one of JWST's most provocative unanswered questions, a class of early universe phenomena sitting entirely outside the boundaries of current theoretical understanding. The anomalies from JWST are not confined to the scales of individual galaxies. They extend to the three-dimensional structure of the universe itself, the large-scale cosmic web of filaments, walls, clusters, and voids that organizes matter on scales of hundreds of millions to billions of light-years. The cosmic web is a consequence of the same density fluctuations that seeded galaxy formation, but amplified over a vastly longer time by the cumulative effect of gravity on enormous scales. Standard models describe the growth of cosmic web structure with mathematical precision, and they set specific limits on how large any coherent connected structure can be. Those limits come from fundamental physics. Density fluctuations grow at a rate set by the balance between gravity and cosmic expansion. The expansion slows the growth of structure. Matter cannot fall together faster than the Hubble flow. The recession of space itself allows. On very large scales, where the gravitational signal has to travel across enormous distances to bring separated regions into coherent motion, structure formation proceeds slowly. The standard model derives a theoretical maximum size for any coherent cosmic structure of roughly 1.2 billion light-years, above which the expansion of space would have prevented the structure from assembling even over the full age of the universe. That limit had already been strained before JWST launched. In 2021, astronomer Alexia Lopez identified a structure called the Giant Arc, a curved arrangement of galaxies and galaxy clusters spanning roughly 3 billion light-years. Located approximately 9 billion light-years away, the Giant Arc is more than twice the theoretical maximum size for a coherent cosmic structure. If it represents a physically connected overdensity rather than a chance alignment of unrelated objects along the line of sight, its existence violates the cosmological principle, the foundational assumption built into the lambda CDM model, that the universe is statistically uniform and isotropic on sufficiently large scales, with no preferred directions or giant concentrated features. JWST has now begun, probing the cosmic web at much earlier epochs, finding proto-clusters, the seeds of future galaxy clusters, at redshifts above 10, within the first 500 million years of cosmic history. These overdense regions, concentrations of galaxies significantly above average density, imply that matter had already clumped substantially in the first few 100 million years. Producing protoclusters this early requires either stronger initial density fluctuations than the standard model produces from the cosmic microwave background seeds, or a faster rate of structure growth than the model allows, or some process concentrating baryonic matter beyond what dark matter dynamics predict. Any of these possibilities requires adding something to the standard framework that is not currently in it. Running parallel to all the structural and compositional anomalies uncovered by JWST is a problem in the measurement of the universe's expansion rate that predates the telescope's launch, but has been confirmed and sharpened by its data. The Hubble constant named for Edwin Hubble, who first characterized cosmic expansion in the 1920s, describes how fast the universe is currently expanding. It is expressed as a velocity of recession per unit of distance. How many kilometers per second of recession you observe for every unit of distance you look out into the cosmos. It is the most fundamental single number in observational cosmology, setting the scale of the observable universe and the age of the cosmos. There are two independent methods for measuring the Hubble constant, and they have been giving different answers for years. The first method uses the cosmic microwave background, measured with extraordinary precision by the Planck satellite. Astronomers measure the temperature fluctuations in the ancient microwave sky, extract the power spectrum of those fluctuations, fit the lambda CDM model to the data, and from that fit, extract all the model's parameters, including the Hubble constant. This method gives approximately 67 kilometers per second per unit of distance. The second method builds up a chain of distance measurements within the local universe, using Cepheid variable stars as distance markers within nearby galaxies, and then Type Ia supernovae to extend the distance scale further into the cosmos. This method, called the distance ladder, consistently gives approximately 73 kilometers per second per unit of distance. The gap between 67 and 73 sounds small, but is not. Both methods have been refined over years to reduce their internal uncertainties. The error bars have shrunk. The two measurements, rather than converging as precision improved, have maintained their separation. The discrepancy now stands at approximately 5 standard deviations, the threshold physicists conventionally describe as sufficient to call something a genuine discovery. A 5 sigma tension means there is less than 1 chance in 3 million that the discrepancy is a statistical accident in both measurements, simultaneously pointing in the same wrong direction. Something is genuinely different between what the two methods measure. For years, many astronomers suspected calibration errors in the distance ladder, specifically in the Cepheid measurements used as its initial rungs. JWST was expected to resolve this by providing far sharper measurements of Cepheid stars in distant galaxies, potentially identifying and correcting systematic errors. In 2023, the JWST-based Cepheid measurements from the SH0ES team, led by Nobel laureate Adam Rees, confirmed the higher value and ruled out several proposed sources of systematic error. The JWST Cepheid data was cleaner than any previous dataset, less confused by crowded stellar environments, and it gave the same answer as the pre-JWST distance ladder. The Hubble constant from the distance ladder is approximately 73. JWST has confirmed that number. The tension with the cosmic microwave background value of 67 is real, not a calibration artifact, and not going away. A 5 sigma discrepancy in the most fundamental number in observational cosmology, confirmed rather than resolved by the most sensitive instrument ever built for the task, means that something in our physical description of the universe is genuinely wrong. The Hubble tension points to a crack in the foundation that the galaxy mass anomalies and the early structure findings are also exposing. All 3 lines of evidence converge on the same uncomfortable conclusion. The standard model of cosmology, as precise and successful as it has been, is producing predictions that conflict with observations across multiple independent physical scales and epochs. The question the scientific community is grappling with is whether this convergence of anomalies requires small revisions to the model's parameters, moderate revisions to its physical descriptions, or something more fundamental. The Hubble tension has a specific structural implication. The cosmic microwave background method extrapolates from the early universe to today using the standard model's physics. If that extrapolation gives a different answer from direct measurement today, either the standard model's physics is wrong in the early universe, wrong in the late universe, or wrong in both. Proposed solutions fall into several categories. One class of solutions introduces what theorists call early dark energy, a component of dark energy that was present in the universe at early times and more significant than the current cosmological constant before fading away. Early dark energy models can shift the CMB-based Hubble constant prediction upward, potentially closing the gap. Another class of solutions modifies the properties of dark matter in the early universe, allowing structure to grow somewhat faster. A third class introduces additional relativistic particles in the early universe that alter the expansion history. None of these proposed solutions has achieved acceptance, partly because each one that helps with the Hubble tension tends to conflict with some other precisely measured quantity. Early dark energy models that raise the predicted Hubble constant to 73 tend to alter the predicted amplitude of temperature fluctuations in the microwave background in ways that conflict with Planck measurements. Models that add extra radiation in the early universe change the expansion rate in ways that affect primordial nucleosynthesis predictions. Every proposed fix to the Hubble tension so far has come with a cost elsewhere, suggesting that the solution, whatever it is not a simple one-parameter adjustment to the existing framework. The fact that JWST was sent to resolve the Hubble tension and returned having confirmed it is itself scientifically significant. It means the problem survived the most precise test of the distance ladder ever conducted. The tension does not live in systematic errors accessible to better instrumentation. It lives in the physics, and addressing it requires identifying which physical description of the universe is wrong and how to replace it. The answer to that question may also be connected to the answer to why early galaxies are too massive, and why early black holes are too large, and why the cosmic web assembled too quickly. These may not be separate problems at all. They may be different faces of a single missing piece in our picture of the universe. The scientific response to JWST's accumulating anomalies has proceeded through several phases. The initial reaction was cautious skepticism. Science has been fooled by surprising early results before, and the standard protocol is to exhaust mundane explanations before invoking new physics. The first proposed mundane explanation for the anomalously massive early galaxies was AGN contamination, and it has partial validity. When a supermassive black hole feeds actively at the center of a galaxy, it pours out radiation across many wavelengths, including infrared, the wavelengths used to estimate stellar mass from photometric data. If an astronomer attributes all of a galaxy's infrared brightness to stars when some of it is actually coming from a nuclear source, the stellar mass estimate will be inflated. This explanation has been confirmed in specific cases. Some of the most extreme JWST galaxy candidates had their stellar masses revised downward after spectroscopic follow-up revealed previously hidden nuclear emission. In those cases, the photometric mass estimates were contaminated, and the revision brought the objects into better agreement with standard predictions. The AGN contamination explanation is real and has resolved the tension for a subset of the most dramatic outliers. It does not, however, resolve the tension for the full population. Many of the anomalous early galaxies show spectral properties dominated by stellar emission with no evidence of significant nuclear contamination. Their mass estimates rest on cleanly stellar light. When the confirmed AGN-contaminated sources are removed from the statistical samples, the remaining population still shows a systematic excess of stellar mass above standard model predictions. The excess is smaller without the most extreme outliers, but it is not eliminated. The overall distribution remains shifted upward. AGN contamination is a real effect that explains some individual cases. It is not a full explanation for the phenomenon. A second proposed explanation centers on the physics of star formation itself. The most sophisticated current simulations of early galaxy formation incorporate feedback from stars and black holes in ways that naturally produce bursty, episodic star formation rather than continuous smooth growth. When a galaxy undergoes an intense star formation burst, it temporarily shines far more brightly than its time-averaged luminosity would suggest. If JWST is catching many early galaxies during such bursts, they would appear systematically more luminous than average, inflating mass estimates based on instantaneous luminosity. The bursty star formation model is physically motivated. Early galaxies had more available gas, less enrichment-driven feedback, and denser environments that favor intense periodic star formation. This explanation has merit for understanding why early galaxies appear so luminous relative to their average properties, but it runs into limits when applied to the most massive candidates. A temporary luminosity enhancement during a burst phase cannot produce the factor of 50 discrepancy seen in objects like JWST 140. The total stellar mass, not just the instantaneous luminosity, is too high, and the chemical evidence, the oxygen in JWST 140 and the nitrogen in GN-Z11, implies stellar histories too deep to be explained by the total stellar mass being lower than estimated. The chemical and structural evidence points in the same direction as the mass evidence. Something fundamental about early galaxy formation was different from what the standard model describes. Beyond adjusting parameters within the existing framework, theorists have proposed more fundamental modifications to the underlying physics. One direction points toward the nature of dark matter itself. The lambda CDM model specifies that dark matter is cold, meaning it moves slowly relative to the speed of light at the time when cosmic structure begins forming. Cold dark matter clusters on all scales, from the smallest dwarf galaxies up to the largest clusters, producing a hierarchical spectrum of structures that builds upward over time. This cold dark matter prediction has been tested against the large-scale distribution of galaxies and the properties of galaxy clusters with considerable success. But on smaller scales, cold dark matter faces persistent challenges. The model predicts many more small dwarf galaxies orbiting the Milky Way and the Andromeda Galaxy than actually observed, a problem called the missing satellites problem. It predicts that dark matter in the centers of galaxies should be concentrated in sharp density peaks, called cusps, but observations often show flatter density profiles called cores. These small-scale tensions have been discussed for decades and are either solved by baryonic feedback processes or by modifying dark matter properties, depending on whom you ask. The early galaxy mass anomalies potentially add to the motivation for modifying dark matter. If dark matter were slightly warm instead of cold, meaning it moved somewhat faster at the time of structure formation, the spectrum of halo masses would shift. Warm dark matter smooths out density fluctuations on small scales, suppressing the formation of the smallest halos while leaving the larger halo population relatively intact. It also potentially allows somewhat larger halos to form earlier, because the smoothing of small-scale fluctuations could allow mass that would have gone into many small halos to instead go into fewer larger halos. This might help with the early galaxy mass problem by providing larger halos earlier in cosmic history. The problem is that warm dark matter models that help with the early galaxy problem tend to predict too few small galaxies elsewhere, creating new tensions while potentially resolving existing ones. The specific temperature of dark matter required to fix one problem tends to break predictions for something else. Finding the right modification to dark matter behavior that resolves the early galaxy tension without creating new contradictions has not been achieved, and may not be possible within the general class of simple, warm, dark matter models. More complex modifications to dark matter physics, involving self-interaction between dark matter particles or dark matter decay, have also been proposed and are under active investigation. A proposal that has attracted particular attention because it potentially addresses multiple JWST anomalies simultaneously is called early dark energy. The standard cosmological constant lambda describes dark energy as a fixed energy density of empty space that has been present throughout cosmic history at the same level. In an early dark energy model, an additional component of dark energy was present and significant in the early universe, around the time that the cosmic microwave background was released, before decaying away or becoming subdominant, leaving the universe looking like the standard model does at late times. The appeal of early dark energy lies in its potential connection to the Hubble tension. The tension arises because extrapolating from the cosmic microwave background epoch to today, using the standard model gives a Hubble constant of approximately 67, while direct measurement today gives approximately 73. Early dark energy models can modify the balance of energy components at early times in a way that shifts the extrapolated prediction upward, potentially closing the gap between the two values. The evidence is concrete. Specific early dark energy models have been tested against the full cosmic microwave background dataset and the large-scale structure of galaxies, and some produce Hubble constant predictions closer to 73, while maintaining reasonable agreement with other observables. Early dark energy may also have consequences for the early galaxy mass problem, because changing the energy content of the early universe slightly alters the expansion history in ways that affect how fast dark matter halos assemble. If early dark energy slightly accelerates the growth of halos in the first few 100 million years, it could, in principle, produce more massive early halos, hosting more massive early galaxies. Whether the amount of early dark energy needed to help with the galaxy mass problem is consistent with the amount needed to help with the Hubble tension, and whether both are consistent with the precise cosmic microwave background measurements, is an active area of theoretical investigation. The challenge with early dark energy models is that they introduce a new component to cosmology with no direct detection. Dark energy itself has no direct detection beyond its gravitational effects on cosmic expansion. Early dark energy would need to be detected or constrained entirely through its gravitational effects on the expansion history and structure growth. Current cosmic microwave background data does not definitively confirm early dark energy models, and some analyses find them in mild tension with the precise Planck temperature fluctuation data. The model is promising and is being actively developed, but it has not achieved the kind of consensus observational support that the cosmological constant itself has. The universe's expansion rate problem and the early galaxy mass problem share a common character. Both suggest that the standard model is producing predictions that are too low at early times. The Hubble constant tension says the universe is expanding faster than the model's early universe parameters predict. The galaxy mass tension says the early universe assembled structures faster than the model's galaxy formation physics allows. The black hole growth problem says early black holes reached enormous masses faster than the model's accretion physics permits. The metallicity problem says early galaxies chemically enriched themselves faster than the model's stellar evolution timelines allow. Every anomaly points in the same direction, faster at early times than predicted. When every anomaly in a dataset points in the same direction, scientists are trained to ask whether they share a common cause. If all of these faster-than-predicted phenomena in the early universe arise from a single underlying physics that the standard model is missing, then fixing that physics might resolve all of them simultaneously. This is the driving motivation behind proposals like early dark energy, modified dark matter, and modifications to feedback physics in galaxy formation. The hope that a single change to the framework might explain multiple anomalies at once. But the proposals that resolve one anomaly completely, while resolving others, only partially have not yet converged on a convincing single solution. Early dark energy helps with the Hubble tension, but does not by itself solve the galaxy mass problem. Modified dark matter helps with small-scale structure tensions, but does not by itself produce the observed early galaxy masses. No single modification so far achieves a simultaneous satisfying resolution of all the anomalies. This might mean that the anomalies have multiple independent causes, or that the right modification has not yet been proposed, or that the solution requires something more fundamental than any parameter adjustment can provide. The scientific community is genuinely divided on how to interpret the accumulation of JWST anomalies, and that division is healthy. It reflects real uncertainty at a scientific frontier where the data is new and the implications are profound. Some researchers see a framework in crisis. Others see a framework under stress that will ultimately survive in modified form. The debate is being conducted publicly, in journals and at conferences, with new data arriving regularly to test and constrain the competing proposals. That is, science working exactly as it is supposed to work at the boundary of knowledge. The scientific debate over what JWST's findings mean for cosmology has a specific texture that distinguishes it from routine scientific disputes. It is not primarily a disagreement about measurements. The observations themselves, the galaxy masses, the spectroscopic redshifts, the chemical abundances, the morphologies, are being confirmed consistently by multiple independent teams using independent methods and independent instrumentation. The debate is about interpretation. What do these observations require us to change in our theoretical framework, and how much of that framework needs to change? The most conservative position, held by a significant portion of the theoretical community, is that the anomalies are real but can be addressed by improvements within the existing lambda CDM framework. Specifically, the argument is that current simulations do not correctly model the detailed physics of star formation and feedback in the early universe, and that better simulations incorporating more realistic feedback prescriptions will naturally produce more massive early galaxies without requiring any modification to the dark matter model or the cosmological parameters. This position is not unreasonable. The simulations used to predict early galaxy properties are sophisticated but not perfect. They rely on approximations for physical processes that occur at scales far below what the simulations can resolve, including the turbulence in star-forming clouds, the propagation of supernova blast waves through inhomogeneous gas, and the detailed feedback from active galactic nuclei on surrounding gas. Improving these subgrid recipes might shift predictions upwards sufficiently to accommodate what JWST finds. The challenge for this conservative position is the scale of the discrepancy. A factor of 50 in stellar mass at the highest redshifts is not the kind of discrepancy that better subgrid recipes are likely to resolve. Subgrid recipe improvements might shift predictions by a factor of 2 or perhaps 3. Moving by a factor of 50 while staying within the bounds of known physics and without violating the fundamental constraints on star formation efficiency requires something more substantial than a recipe adjustment. The conservative position is most defensible for moderate redshift anomalies, and less defensible for the extreme objects at the highest redshifts, like JWST-140, that represent the sharpest confrontations between observation and standard theory. The intermediate position, growing in support, is that the lambda CDM model's cosmological backbone, its description of dark energy, dark matter, and the universe's overall geometry and expansion history, is correct, but that the galaxy formation model embedded within it needs substantive revision. This revision might involve significantly higher star formation efficiencies in early massive halos, driven by physical conditions in the early universe that current simulations do not capture. It might involve different feedback timescales for early galaxies compared to modern ones. It might involve a revised description of how dark matter halos acquire and retain baryonic material at early times. This intermediate position preserves what the model gets right, which is a great deal, while acknowledging that the galaxy formation component is genuinely challenged by the data. At the more radical end of the interpretive spectrum, some researchers have argued that JWST's findings point toward a need for new physics at the fundamental level. This position takes the convergence of anomalies, the galaxy masses, the black hole sizes, the metallicities, the morphologies, the Hubble tension, and asks whether they could all be symptoms of a single physical description that is genuinely missing from the standard model. One candidate for that missing physics is a modification to the behavior of gravity itself on cosmological scales. Modified Newtonian dynamics, developed by Mordechai Milgrom in the 1980s, proposes that gravity behaves differently at very low accelerations than Newton's law predicts. In MOND, below a certain acceleration threshold, the gravitational attraction falls off more slowly with distance than in standard gravity. The original motivation was explaining galaxy rotation curves, the observation that stars in the outer regions of spiral galaxies orbit too fast to be explained by the visible mass under Newtonian gravity. MOND can explain many galaxy rotation curves without invoking dark matter. Some researchers point to JWST's early massive galaxies as further evidence for MOND or related modified gravity theories, arguing that a different description of gravity in the early universe could allow structure to form faster than lambda CDM predicts. Modified gravity theories face significant challenges. The cosmic microwave background fits the lambda CDM model with dark matter so precisely that any modified gravity theory must reproduce all those fits simultaneously, which turns out to be very difficult. Most modified gravity models require additional scalar fields or modifications to general relativity that introduce free parameters, and constraining those parameters against the full range of cosmological observations leaves little room for significant deviation from the standard model. The few modified gravity theories that fit the CMB data tend to reintroduce something functionally equivalent to dark matter through a different mathematical description, raising questions about whether they represent a genuine alternative or merely a reformulation. A broader class of new physics scenarios involves modifications to what happened in the very early universe, before and around the time of the Big Bang. If the universe underwent a different history of expansion or phase transitions in its first moments, that history could have left an imprint on the initial conditions of structure formation that would produce systematically more structure at early times. Proposals of this kind are diverse and range from modifications to cosmic inflation, the hypothetical period of exponential expansion very early in the universe's history, to primordial magnetic fields, to acoustic features in the dark matter power spectrum. All of these proposals face the constraint that any modification to the early universe must remain consistent with the extraordinarily precise CMB measurements, which limits how much the initial conditions can be altered. Among JWST's most anticipated and most elusive scientific targets are the universe's very first stars, the population 3 stellar generation, whose existence is theoretically predicted but which has never been directly observed. The entire history of the universe's chemistry depends on the first stars. They ended the Dark Ages, produced the first heavy elements, and seeded the gas from which all subsequent stellar generations formed. But detecting them directly has been beyond the reach of every telescope before JWST, because they existed so long ago and their light has been so severely stretched by cosmic expansion that it arrives today in wavelengths requiring the specific sensitivity that only Webb can achieve. In 2023, observations of a gravitationally lensed source called the Sunrise Arc offered what may be the first glimpse of population 3 star clusters. Gravitational lensing occurs when a massive galaxy cluster in the foreground bends and amplifies the light from a more distant object behind it, acting as a natural cosmic magnifying glass. The Sunrise Arc is a distant galaxy whose light has been amplified by such a lens, allowing JWST to see far fainter details than it could in direct imaging. Within the arc, the JWST team identified a compact region of star formation with properties matching theoretical predictions for population 3 stars. Extremely high stellar temperatures, powerful ionizing radiation output, and no detectable heavy element absorption in its spectrum. These properties are consistent with a cluster of massive metal-free stars burning at the extreme temperatures expected for the first stellar generation. The detection was described as tentative. Alternative explanations involving very young star clusters of the second stellar generation, still relatively metal-poor but not entirely metal-free, were not definitively ruled out. Distinguishing definitively between truly metal-free, population 3 stars, and nearly metal-free second-generation stars requires spectroscopic data of sufficient depth and quality to detect or rule out even trace heavy element absorption, which pushes the limits of JWST's capabilities on objects this faint even with lensing amplification. If the Sunrise Arc detection or a subsequent confirmed detection proves to be genuine population 3 stars, it would represent one of the most profound observational achievements in the history of astronomy. Seeing the universe's very first stars would close the last observational gap in the story of cosmic dawn, providing direct confirmation that the Dark Ages ended through stellar ignition and giving the first direct measurement of the properties of metal-free stellar populations. It would also constrain the models of early star formation more tightly than any theoretical prediction can, potentially revealing whether population 3 stars were indeed as massive and extreme as current models suggest. Among the subtler, but no less significant JWST findings is a population of early galaxies that have already stopped forming stars at epochs when the standard model says they should just be beginning their most active phase. Astronomers call this quenching, the cessation of star formation in a galaxy. A galaxy quenches when it has exhausted its available gas supply, or when some process heats or expels that gas before it can form stars, cutting off the fuel for further stellar production. In the nearby universe, massive elliptical galaxies are mostly quenched. They formed the bulk of their stars billions of years ago and have since been declining in activity, their stellar populations aging quietly without renewal. Standard models place the quenching of massive galaxies late in cosmic history. The typical massive elliptical galaxy in the nearby universe quenched its star formation several billion years ago, after a period of vigorous activity that preceded it. The feedback processes that drive quenching, primarily the energetic outflows from supermassive black holes as they accrete material, require time to build up. The black hole has to grow large enough and active enough to drive feedback strong enough to expel the galaxy's gas supply. This process plays out over billions of years in most standard scenarios. JWST is finding massive galaxies that have already quenched at redshifts above 4, 5, and even 6, when the universe was less than 1.5 billion years old. The most extreme cases, galaxies that appear to have already quenched by 1 billion years after the Big Bang, must have assembled their stellar mass, built up a massive central black hole, activated feedback strong enough to expel or heat their gas supply, and then gone quiet, all within the universe's first billion years. The compressed life cycle these objects represent, from active star formation to dead galaxy in under a billion years, is not well reproduced by any current simulation. The quenching anomaly adds another dimension to the picture of early cosmic overefficiency. The standard model says the early universe should be slowly assembling its first galaxies. JWST is finding that the early universe was assembling and completing galaxies, taking them through their full life cycle from star forming to quenched, at a pace that the model assigns to a much later epoch. Fast formation and fast quenching together suggest that whatever mechanism drives the life cycle of galaxies operates faster in the early universe than in the late universe, which again points toward conditions in the early cosmos that the standard model does not adequately capture. Stepping back from any individual observation and looking at the full picture painted by JWST's first few years of science operations, a single, consistent theme emerges with clarity that is difficult to dismiss. The early universe was more productive than theory said it could be, more structurally mature, more chemically complex, more gravitationally organized on both small and large scales, more efficient at completing processes that models predicted would take much longer. The galaxy mass anomaly says this clearly. Galaxy after galaxy, in the first few 100 million years, shows stellar masses 10, 20, 50 times above what lambda CDM predicts. The metallicity anomaly says this in chemical language. Heavy elements appear at epochs when standard stellar evolution timelines say they should be barely beginning to accumulate. The morphology anomaly says this in geometric terms. Ordered, rotating disk galaxies appear in numbers 5 times higher than predicted in the universe's first 3 billion years. The black hole mass anomaly says this through the physics of accretion. Central black holes in early galaxies reach masses that require near maximum accretion from the very beginning of their existence. The quenching anomaly says this through cosmic archaeology. Galaxies that have already completed their entire active lifetimes appear at epochs when the standard model says they should just be starting. The large-scale structure anomaly says this at the grandest scale. The cosmic web is assembling coherent structures earlier and at larger sizes than the theoretical maximum permits. The Hubble tension, the 5 sigma discrepancy in the universe's expansion rate, says this in a different register, but the same key. The universe appears to be running at a different tempo than the standard model computes from first principles. The consistency of direction across independent observational probes is the most scientifically significant aspect of the problems. Full JWST picture. Random measurement errors scatter in both directions, producing some results above predictions and some below. Systematic biases in instrumentation typically affect specific measurement types and not others. When galaxy masses, chemical abundances, galaxy shapes, black hole masses, large-scale structures, and expansion rate measurements all simultaneously deviate from predictions in the same direction, the most parsimonious interpretation is not that 6 independent measurement types all happen to be systematically biased in the same wrong direction by different amounts through different mechanisms. The most parsimonious interpretation is that the theoretical predictions are systematically wrong for the early universe in a consistent way. Finding what is wrong and fixing it is the central challenge facing observational cosmology. In the coming decade, JWST has both sharpened the challenge by making the anomalies observationally precise and provided the foundation needed to work toward an answer by building a rich catalogue of confirmed early universe objects against which any proposed theoretical revision can be tested. The challenge is real. The tools to address it are more powerful than anything available in any previous era of cosmological inquiry. The answer, whatever it turns out to be, will be worth finding. The scientific community's honest assessment of where things stand is more nuanced than popular science coverage often conveys. Headlines announcing that the Big Bang has been disproved or that everything cosmologists knew was wrong misrepresent the situation in ways that serve excitement at the expense of accuracy. The Big Bang itself, understood as the hot, dense origin of the universe and its subsequent expansion, is not challenged by any JWST finding. The evidence for it from multiple independent sources is overwhelming and untouched by anything Webb has observed. Big Bang nucleosynthesis is the clearest example. In the first 3 minutes after the Big Bang, nuclear reactions produced hydrogen, helium, and trace lithium in specific proportions determined by the temperature, density, and duration of the conditions that existed. Those proportions, about 75% hydrogen and 25% helium by mass, have been measured in the oldest, most chemically primitive stars and gas clouds in the universe, and agree with the Big Bang prediction to better than 1% across a range of elements and isotopes. No observation from JWST challenges this. If the Big Bang had not happened, or had happened differently, the nucleosynthesis products would be different from what we observe. They are not different. The cosmic microwave background provides equally firm support. The universe was hot and dense enough to be an opaque plasma, and when it cooled and the plasma cleared, it left a specific afterglow with specific properties that JWST's findings do not challenge. The large-scale temperature fluctuations in the microwave sky match the lambda CDM model's predictions with extraordinary precision at large angular scales. The overall geometry of the universe, the evidence from multiple independent observations that it is spatially flat, is not challenged. The discovery and confirmation of dark energy through the acceleration of cosmic expansion, first observed by supernova surveys in 1998, is not challenged. What is challenged is the detailed model of how matter organized itself into galaxies within this established Big Bang framework. The subfield of galaxy formation theory, which describes the specific physical processes that convert dark matter halos and baryonic gas into the galaxies we observe, is what JWST is stress testing. That subfield is not the foundation of cosmology. It is a structure built on top of the foundation. JWST may be showing that the structure needs to be rebuilt on the foundation, not that the foundation itself needs to be replaced. The history of astronomy offers both context and comfort for the current moment of uncertainty. Every generation of astronomers has encountered a universe that turned out to be stranger, larger, and more complex than the previous generation expected. Each encounter seemed at first like a crisis, and ultimately proved to be an expansion of understanding that enriched rather than replaced what came before. Edwin Hubble's 1925 proof that the spiral nebulae were separate galaxies vastly farther away than the Milky Way transformed the cosmos from a single island of stars into a universe of billions of galaxies, stretching to distances no instrument could then reach. Before Hubble's observations, the Milky Way was generally believed to be essentially the entirety of the universe. The existence of galaxies beyond it was debated and disputed by the astronomical community. After Hubble's observations, the Milky Way shrank from the whole cosmos to a single, unremarkable galaxy among hundreds of billions. The revision was total and irreversible, and it made astronomy immeasurably richer. In the 1990s, the JWST, two independent teams measuring the distances and recession speeds of type Ia supernovae in distant galaxies, expected to find evidence that the universe's expansion was slowing down under gravity. Both teams independently found the opposite. The expansion was accelerating. Something was pushing space apart. Neither team could identify what that something was. It was given the name dark energy. It turned out to compose 68% of the universe's total energy content. The revision was so fundamental that both team leaders received the Nobel Prize in Physics. Nothing in the lambda CDM model before those observations had confidently predicted dark energy. The model was extended to incorporate it, and the extended model became the most successful cosmological framework ever built. What appeared to be a crisis became the cornerstone of modern cosmology. Both of these examples share a common structure with what JWST is presenting now. Confident predictions, carefully derived from the best available theory, conflicted with precise observations. The conflict was resolved not by abandoning the underlying framework, but by extending it in ways that incorporated the new observations. The extensions made the framework more accurate, more complete, and more predictive than what preceded them. The same pattern is likely to apply to whatever JWST is currently revealing. The universe's early behavior, too active and too structured too early, will be explained. When it is explained, the explanation will tell us something new and important about the physics of the cosmos that we did not know before. The Big Bang will still have happened. The standard cosmological model will still describe most of what we observe with great accuracy, and the early universe will be better understood than it has ever been. JWST is still in the early years of its science mission. Its design lifetime is 20 years, and the precision of its launch and the efficiency of its operations have extended its projected fuel lifetime potentially well beyond that. Each year of continued operations adds depth to existing surveys, provides spectroscopic confirmation for additional photometric candidates, and opens entirely new windows through programs that have not yet been scheduled. The pipeline of data coming from the telescope is not slowing down. If anything, it is accelerating as survey programs enter their most productive phases and as the community develops new techniques for extracting information from the data. Among the highest priority, remaining targets are candidate galaxies at redshifts above 15 within the first 200 million years after the Big Bang that have been identified in photometric surveys, but not yet confirmed spectroscopically. If any of these candidates are real, they would push the boundaries of early universe observations even further and tighten the constraints on every proposed explanation for the early galaxy mass anomaly. Spectroscopic confirmation at these extreme redshifts pushes JWST to the limits of its sensitivity and requires very long integration times. But the science motivation is high enough that programs targeting these objects have been approved and are being executed. Gravitational lensing programs continue to reveal objects that would be invisible to JWST without the amplification provided by foreground galaxy clusters. The most magnified lensed sources can be studied in detail that would otherwise require a telescope many times larger than Webb, effectively giving astronomers access to galaxy properties at high redshifts that unmagnified surveys cannot reach. These programs have already provided the tentative population 3 detection and have revealed extremely faint early galaxies in multiple fields. As the catalogue of well-characterized lensed sources grows, the statistics on the faint end of the early galaxy luminosity function will improve, answering one of the key open questions about whether there are far more low-mass early galaxies than models predict, in addition to the excess of high-mass ones. The galaxy morphology studies are also continuing to grow in the statistical power. The finding that roughly half of early galaxies show disk morphology was based on a sample large enough to be statistically significant, but not large enough to definitively characterize all morphological subclasses. Larger samples will reveal whether the disk fraction varies with mass or redshift in ways that constrain the physics of early disk formation. Higher resolution spectroscopy of the disk galaxies that have been identified will measure their rotation curves and assess how dynamically mature they really are, potentially revealing whether these early disks are truly analogous to modern spiral galaxies or represent a different physical class that merely resembles them in morphology. The broader scientific community has responded to JWST's early universe findings with a mixture of excitement and methodological rigor that represents the scientific process at its best. The findings are being replicated across independent survey programs and confirmed by independent analysis teams. When multiple groups using different datasets, different analysis approaches, and different assumptions about stellar populations and dust properties arrive at the same conclusion, confidence in that conclusion grows substantially. The early galaxy mass excess has now been found by enough independent groups that the observational reality of the anomaly is accepted even by researchers who dispute its theoretical interpretation. The theoretical response has been, quote, equally productive. The anomalies have motivated new classes of simulations, specifically designed to test whether modifications to feedback, physics, dark matter properties, or initial conditions can reproduce the observed early galaxy population while remaining consistent with all other cosmological constraints. High-resolution zoom-in simulations targeting the most massive early halos have revealed that the complex interplay of gas dynamics, stellar feedback, and chemical enrichment in extreme environments is not fully captured by the subgrid prescriptions used in earlier cosmological simulations. Some of these new simulations produce early galaxy populations that match certain aspects of JWST's findings better than earlier work did. None has yet achieved a complete simultaneous resolution of all the anomalies within a coherent physical framework. New observational programs are being designed specifically to test the predictions of competing theoretical explanations. If bursty star formation is the dominant explanation for anomalously luminous early galaxies, those galaxies should show specific spectral signatures of recent rapid star formation events. If AGN contamination explains some of the mass excess, systematic spectroscopic programs can characterize the AGN fraction in early massive galaxies and correct for its contribution. If modified dark matter is the answer, specific predictions for the small-scale clustering of early galaxies differ from those of cold dark matter models in ways that deep JWST surveys can eventually measure. The observational programs to test these predictions are being planned and executed, adding targeted tests to the flood of general survey data. The overall picture is of a field energized by genuine discovery. The standard model is under pressure, but the pressure is being applied through the mechanism that science requires. Precise observations that disagree with precise predictions forcing both better observations to confirm the disagreement and better theory to explain it. The disagreement is telling cosmologists something real about the universe, something that was invisible before JWST and is now unavoidable. Working out what that something is will require years of observation, theoretical development, and argument. The outcome will be a description of cosmic history more accurate and more complete than the one we currently have. What JWST is doing to cosmology is something that happens rarely but repeatedly in the history of science. It is revealing that a physical description we were confident in does not fully match reality. Every confirmed discrepancy is a scientific gift. Every confirmed discrepancy between observation and theory narrows the range of possible physical descriptions of nature. Every anomaly is a constraint. Every surprise is a clue. The universe, at its earliest epochs, is behaving differently from the standard model's predictions, and that difference is a message. Decoding the message requires understanding exactly how the behavior differs, exactly how consistently it differs across independent observations, and exactly what physical changes could produce the observed differences while keeping the framework consistent with everything else it correctly describes. The galaxies that are too massive, the black holes that are too large, the chemistry that is too advanced, the disks that are too organized, the structures that are too big. Each of these is a data point in a pattern. Patterns carry information. The information these patterns carry is not yet fully decoded, but the decoding has begun, and the tools available, both observational through JWST and theoretical through increasingly sophisticated simulations and analytical methods, are more powerful than anything available in any previous era of cosmological inquiry. Future facilities will extend JWST's work. The Extremely Large Telescope, a ground-based 39-meter mirror being built in Chile, will provide spectroscopic capabilities on extremely faint, high redshift sources that complement JWST's imaging strength. The Nancy Grace Roman Space Telescope, a NASA space telescope with a field of view 100 times larger than Webb's, will survey enormous areas of sky at near-infrared wavelengths, building the large statistical samples needed to test rare object predictions from modified theories. The Euclid Space Telescope, already in orbit, is mapping the large-scale distribution of galaxies across billions of light-years, providing the cosmic web data needed to test large-scale structure predictions from competing models. All of these facilities will be asking the same questions from different angles, and their combined output will place the current JWST anomalies in a context that should eventually allow a definitive assessment of what they mean. The convergence of multiple next-generation facilities on the same fundamental questions about early cosmic structure means that the period ahead may be the most information-rich era in the history of cosmological observation. The resolution may come from within the standard model, through better understanding of galaxy formation physics, or it may require extending the model in ways that change what we understand about the universe's fundamental composition or its earliest moments. Either outcome advances human knowledge. Either outcome represents the scientific process succeeding at its core purpose. We built the most powerful telescope humans have ever launched into space, pointed it at the oldest darkness in the universe, and what came back told us that the story we had been telling about the universe's beginning was incomplete in important ways. The galaxies that should not exist, the black holes that should not have had time to grow, the chemical enrichment that should not have happened so early, the organized disk structures that should not have formed in the universe's childhood. All of these are messages from the earliest epochs of cosmic history, arriving in the infrared light that Webb was designed to catch, telling us that the universe was doing things in its first 300 million years that our best models did not allow. Cosmology is deepening. The Big Bang happened. The universe expanded from a hot, dense state. The cosmic microwave background records the plasma phase with extraordinary precision. Nucleosynthesis produced the elements correctly. The large-scale structure of the universe on the grandest scales matches the standard model remarkably well. The foundation is solid. What JWST is showing is that the universe built something extraordinary on that foundation, faster and more efficiently than any of us predicted. And understanding how it did that is the next great challenge in the human effort to understand the cosmos. The answer will require better simulations, more data, new theoretical ideas, and probably some discoveries we have not yet imagined. It will require the community of researchers who are currently arguing over whether the standard model needs small tweaks or fundamental revision to keep looking, keep measuring, keep running the numbers, and keep confronting the results against the data. That process is already underway. Webb is still working, still sending back data, still finding objects that require explanation. Among the lessons the telescope has already taught is this: the universe does not simplify as you look harder at it. It grows more complex, more layered, more full of phenomena that require new thinking to explain. Every generation of astronomers who pointed a more powerful instrument at the sky found a cosmos richer and stranger than the one they expected. Webb is continuing that tradition in the most literal possible way, reaching farther back in time than any previous instrument, finding a universe that was already rich and strange in its very first moments. The earliest light from the most distant galaxies ever seen by human instruments is carrying a message to us across nearly 14 billion years of cosmic history. The message is not one of disorder or confusion. It is one of extraordinary, improbable productivity in the universe's first moments. Hundreds of millions of stars forming where models said almost none should be. Chemistry emerging before models said the ingredients were ready. Organization appearing before models said the chaos had subsided. Black holes growing to sizes that the physics of accretion should have made impossible. The universe at its dawn was not the humble beginning the textbooks described. It was already building something remarkable, and we are only beginning to understand what that means for the full story of how everything came to be.